Chapter 16, the atmosphere. Often, we don't really pay too much attention to the atmosphere that surrounds us every day. I show this picture to start out with on this slide because it's a situation where my dad and I were scuba diving in Key Largo during the winter, and you're in this situation where you have to pay so much attention to your surrounding environment. You have to pay attention to the water because you can't breathe from it, so you have to make sure you have oxygen with you. You're also paying attention to how cold it is and how easily you can float. And instead of just being able to naturally move around this environment, your brain is constantly thinking about it. So as we're starting to learn about the atmosphere, remember that you are constantly surrounded by the atmosphere we're talking about, but often take it for granted because there's no need to really pay too much attention to it. So we're going to try and key in on some things that we already know about the atmosphere and just pay a little more attention to it. During the lab, we're going to be doing a lot of hands-on activities, and we're going to be looking at concepts that we can try and delve into and get a better grasp on. A lot of the PowerPoints, the Camtasia lectures, are actually mostly definitions of words that you should understand coming out of this class. So here we're going to look at two words, two terminologies that we should understand the definitions for and be able to distinguish between. We have weather versus climate, and often these are used as a similar term. However, they have very specific different definitions. Weather is a very dynamic process that occurs at a given time and place, and it's always changing. Whereas climate looks at the aggregate weather conditions in a certain area, and this is based on many years of observations. The big difference between weather and climate is that climate takes into account the average of the weather plus the extremes. So if you were going to go on a trip next week to Florida, you would be interested in what the weather is going to be like next week. However, if you wanted to take a trip next December in Florida, you would probably be looking up climate information because you can't get weather information that far in advance. But instead, you would be interested in what is the climate? What are the extremes at that time of the year? How cold could it possibly get? How warm could it possibly be? So, another way to think about it is if you were packing for a vacation, you're probably going to pack based on the weather. But if you're packing for moving to a new location, you're probably going to want to know what the climate is there so that you pack for all of the events that you might find. Another important thing to notice about the climate is the fact that it takes into account the extremes of weather. This shows you how much the climate varies throughout the seasons. If the extremes of the weather are close in range, then you know you're going to have a consistent climate. If the extremes in weather are very far in range, then you know you'll have a lot of different seasons and a lot of different weather patterns in that area. So when we're looking at weather and climate, there are some common measurements that we use. You're probably familiar with most of these. Air temperature, usually in Celsius or Fahrenheit. Humidity, which while you might have heard of that term and used it, we're going to actually learn later on exactly what humidity is. Probably used it in saying, it's so humid my hair is so frizzy, or so humid I'm just keep sweating to death. Those are terms that do describe humidity, but we'll learn it a little bit more in depth later on. Obviously, types and amount of cloudiness and precipitation, air pressure, and speed and direction of the wind. So as we start to talk about the atmosphere, it's important to learn about its structure. And we're going to separate 4 layers of the atmosphere based on temperature. We're going to start at the surface and work our way to outer space. The surface is the troposphere, and the troposphere is where we live. So most of the times when we're thinking about weather and climate, we're going to be thinking about the troposphere. Troposphere is thin, but it's really important because this is where all of life exists. It's also where the weather processes occur. As you know, if you climb up a mountain or you look to the top of a mountain and see snow up there, it's often colder as you ascend in height. And in general, in the troposphere, the temperature changes negative 6.5 degrees, so it decreases 6.5 degrees Celsius for every kilometer. And while the troposphere can vary in thickness, it's often 12 kilometers thick. It can vary based on density of the air and also what the topography is at the surface. Are there mountains? Are you in Louisiana where you're already at sea level? That'll all change the thickness of the troposphere. The next layer is the stratosphere, and the key, most important part about the stratosphere is this is where the ozone layer exists. I'm sure you've often heard about the hole in the ozone layer, and we'll talk about it a little bit more. Well, what's important about the ozone layer is that it keeps ultraviolet rays from the sun out. Ultraviolet rays are deadly to our skin, and without them being kept out by the ozone layer, humans would not be able to live on the Earth. In general, it increases in temperature as you increase altitude, so it's the opposite of the troposphere. The next layer is the mesosphere, and this is a very cold layer, negative 90 degrees Celsius. There aren't many molecules here, and it's actually least explored just because it's kind of smack in the middle of the layers. It's hard to get data from it if you start at the surface, and it's hard if you have an orbiting satellite to try and get data from it since the thermosphere is in the way. In this area, space junk is burned off. You may have heard about space junk in news articles or on the web. And space junk is not a new phenomenon, but we have new occurrences with the sun that are causing the space junk, debris from satellites and other material that's out orbiting our Earth. This debris is starting to fall to the surface of our Earth. The reason for this is that the sun is experiencing a high sunspot density. Sunspots are very bright portions of the sun. And so this is adding more heat to our thermosphere. The thermosphere is then getting less dense as it heats up. However, the particles from the space junk are not losing density, and so they are, in relation to the atmosphere out there, they are getting heavier, and they start to fall to the Earth. As they fall, parts of them will be burned up in the mesosphere, but the larger particles will make it to Earth. They're very hard to predict where they're going to fall because of the oddity of their shapes. They often have things that kind of look like sails, and they will act as sails when they hit certain winds in the upper atmosphere. You can see a picture on the top here. This is a space shuttle that had fallen to Earth, and you can see that we don't have all the pieces and particles, and this space shuttle was hunted for, so a lot of the pieces and particles burned up as it crashed to Earth, and it burned up through the mesosphere. This is also why we don't have many meteors hitting the Earth. We do get a few, but not as many. Our Earth isn't as cratered as something like our Moon or Mercury, which lack an atmosphere. And the mesosphere is the main portion where they're all going to get burned up. Last but not least is the thermosphere, and I have To Infinity and Beyond, a little Toy Story reference there. In the thermosphere, there isn't a real good definition between the thermosphere and outer space. The particles just get less and less dense until you're in outer space. It's very sparse out here. However, technically, the particles are moving around so fast that it is actually very hot, over 1,000 degrees Celsius. But if you put your hand outside there, particles wouldn't hit your skin very often and you would feel cold. This is the location where satellites orbit, and it's also the area where the auroras or the northern lights are produced. Again, these 4 layers are based on the thermal structure of the atmosphere. As you can see in this picture, the temperatures change, go back and forth and back and forth. However, the main portion we will be talking about throughout the rest of the semester is the troposphere. This is where we live, and this is where weather occurs. You can see in the troposphere it gradually decreases temperature at negative 6.5 degrees Celsius per kilometer. Therefore, a lot of times when we're talking about ascending in height, we can assume that the temperature is decreasing for any of the processes of weather that we're discussing. Here's some more terminology, more definitions that you should be aware of when talking about air temperature. You'll hear these if you watch a weather report. Often people are interested in what's the daily maximum and minimum temperatures, and also what's the daily mean temperature, which is just a maximum and minimum divided by 2, or the daily range, which is the difference between the maximum and the minimum. We can also look at temperature based on monthly mean or an annual mean. So looking at it over the average of a month, or the average of a whole year. Another important temperature measurement is the annual temperature range, and this is the difference between the highest and lowest monthly means. Again, this can go back into determining what our climate is like and how varied of a climate it is. If the range is small, then you're going to have similar climate throughout the whole entire year. But if the range is wide, then that means you're going to experience a lot of different systems and seasons throughout the whole year. So what actually controls temperature at a certain location? Here are two places, Vancouver and Winnipeg, and then New York and Eureka. These both exist at similar latitudes. Most of the time, people think it's warm at the equator, cooler at the poles. And while this is a general description that somewhat holds true, it doesn't always hold true. So on the top left picture, you can see that the red line for Vancouver has much smaller temperature range over a year than the blue line for Winnipeg. What you're looking at here are called climographs. And climographs show on the bottom the months over a year, and then on the sides it shows temperature. And so you can kind of map out a whole entire temperature scheme for a whole year. On the right-hand side, you can see that the red line has a smaller temperature range also than the blue line. Why, if these are at the same latitude, are they experiencing different temperature range? And the answer is in the parentheses. Vancouver receives a lot of maritime or marine winds, and it has a marine climate. So the ocean tends to equalize out the extremes in temperature. Whereas Winnipeg is in the center of the continent, it doesn't have an ocean, and it's much more vulnerable to changes in temperature from the sun. On the right-hand side, Eureka, California is on the windward side, again receiving wind from the ocean, which keeps it at a moderate climate, while New York City is receiving wind from the continents, and so it is very much more vulnerable to fluctuations in temperature. So sometimes, even if a temperature is given by a thermometer, humans have a different perception of temperature. Technically, temperature is the rate of heat loss which influences sensations of temperature. So as your heat is lost, it can change how you think something feels. So if it's windy, the wind starts to move air particles away from your body. And so you're constantly getting air particles around your body are heated up by your body heat, and then they're moved away. So then your body has to heat up another layer of air around your body, and then that's moved away. And so that's when you get a feeling of being colder because the wind is sweeping the warm particles away from you. Obviously, air temperature does play a part in how hot you feel, and relative humidity plays a major role in whether or not you feel warm. Sweating is one of the main ways that humans cool off. If humidity is high, when people sweat, the sweat cannot be evaporated into the atmosphere because the atmosphere already has moisture in it. Therefore, the sweat stays on your skin instead of evaporating. The process of evaporation is what cools you down. Therefore, if you sweat and the sweat beads do not evaporate, you won't feel warm. In this case, if relative humidity is high, it makes you feel hotter. And then sunshine. We all know on a cold day we like to stand in the sun because that makes us feel a little bit warmer because we're receiving the radiant heat than if we stand in the shade. Here's another term to remember. It's called isotherm. We're going to learn a couple of things throughout the semester called ISO. And ISO are bars. So they're the lines you see drawn on this map. Therm refers to temperature. So these lines refer to bars of temperature. And what they do is they connect areas of equal temperature. And they create what we call a contour map of temperatures. So you can see any area in green has a similar temperature, and any area in between the lines between 90 and 85 in red have a similar temperature within 5 degrees of each other. If you note, the temperatures do not, again, follow latitude. but you have a big curve in the temperatures over in the Midwest. This is most likely due to the effects of the mountain range that's there. We have some generalized terms or generalized patterns of global temperature that we can talk about. In the southern hemisphere, the isotherms, those lines or bars of temperature, are straighter. It's more stable there. And this is we have a lot of water, and water helps to moderate the temperatures. In the northern hemisphere, the lines are more varied, and this is due to land masses. Land masses heat up quick and cool down quick, which ends up changing the temperature much more frequently than when you're looking at areas that are over water. Since the water does reflect different changes in temperature sometimes, this shows that the isotherms can show where ocean currents are moving from. Here's a picture showing world mean sea level temperatures. So this is showing the temperature of the atmosphere at sea level. As you can see, there is less variation in the southern hemisphere. Even though in July, you can see that even though the southern hemisphere is in winter, its temperatures aren't nearly as cool as the northern hemisphere is in January. Again, this is due to the moderation of ocean water. Another thing that we can make an assumption or a generalization about is the annual temperature range. Generally, at the equator, the temperature range is smaller. Typically, the equator stays pretty constant, staying pretty warm. This is due to the incoming solarization. And then as you get higher and higher in latitude, so the equator is actually 0 degrees latitude. As you go to either of the poles, which are 90 degrees north or 90 degrees south latitude, so as you're increasing the latitude number from 0 to 90, the temperature range increases. And also, the temperature range is greatest over continental locations, and this is due to how the continents heat and cool throughout a day. But we know, as we saw in the picture before, the graphs of areas at same latitudes, that latitude is not the only thing that affects temperature. So we're going to go through and look at a few other things that affect temperature. We already mentioned latitude does affect temperature. It is due to the sun angle that's coming into the Earth. Areas at the equator get more direct sunlight than areas at the northern or southern hemispheres. Temperatures are also controlled by altitude. As you increase in altitude, in general, temperature decreases. Another control on temperature is called albedo. This is probably a new term. Albedo is the reflectance of an object. So if you have a glacier, that object is going to reflect. It's going to have a high albedo. But if you have a surface such as a blacktop or a black rock, it's going to absorb sunlight. And so it's going to have a low albedo. And it's going to heat up faster because the sunlight is being absorbed into that material. We're going to do a lab on this. So if you don't quite get this concept yet, don't worry about it. We're going to get into more depth on it later. Land versus water also controls temperature. You probably have experienced being at the beach on a sunny day, and the water is pretty cool. But as soon as you stick your foot onto the sand, you have to run across the sand because your feet start to burn. This is because land absorbs radiation at the surface, whereas water lets radiation penetrate throughout the whole entire water body before it starts to heat up. If you ever dig down into the sand on a sunny day, you get to cooler sediment because the heat only really heats up the surface and it doesn't heat up the sand below as much. In this way, it allows water to moderate the extremes of temperature. In addition, land will also lose heat quicker. So at night when you go out to the beach, the water, even though it might perceptually seem different, it's still pretty much the same temperature as it was during the day. But now, the sand will be very cool as you walk across it because it's lost all its heat to the atmosphere. Additionally, geographic position can control temperature. Geographic position just means where are you on the Earth. You can be on the windward coast, so you can be on the side of a coast that you're having wind coming across the ocean, and the ocean wind is bringing in cool air. Be on the leeward coast where you're getting air from the continents that's heated up all day and therefore warm. We also experience something called the lake effect, especially by the Great Lakes. Often upstate New York will have extreme snowfalls, and this is due to air coming over the Great Lakes, cooling down and starting to precipitate. It picks up moisture and then the air is cooled so it's able to snow. And another major geographic entity that controls weather, controls temperature, is mountains. On one side of a mountain, as the air rises, it cools down and precipitation occurs. We're going to learn about this more later on. But on the other side of the mountain, as air descends, it warms up, but it has no precipitation, has no moisture in it, so it's warm and dry air. This is called a rain shadow. This happens in California and Washington, and it also happens out in Hawaii. The next variable we're going to talk about is atmospheric pressure. And atmospheric pressure is literally the amount of air above you that's pushing down on you, and this is based on gravity. At sea level, we measure the atmospheric pressure at about 1,000 millibars. As you go up in height, there's less molecules of air above you, and so the pressure decreases with height. It doesn't increase linearly, it decreases exponentially because the particles above have more room to move out. So what makes up our atmosphere? Atmosphere, we have constant components and very variable components. Constant components don't change that much. As you see in this picture, our atmosphere is mainly made up of nitrogen and oxygen. Almost 99% is made up of nitrogen and oxygen. Argon is an inert gas, which means it doesn't really react with anything. We don't talk about it that much. It makes up less than 1%. And surprisingly is that carbon dioxide makes up about 0.04% of our atmosphere. And it can change, as we know, with global climate change and increased industries, but on general it stays right around that 0.04%. When we're talking about variable components of atmosphere, we're talking about things that change greatly over the span of a couple of minutes or hours or days. So the main one is water vapor, clouds and precipitation. These things you can look out of your car window one moment and see tons of clouds, and 2 minutes later they could be gone. So these change a lot. They're important in our atmospheric heat because they absorb heat and they release heat as they're formed and as they're precipitated or as they disappear. So they control the heat in an area. Another variable component is what's called aerosols. These are just microscopic particles of solids and liquids suspended in air. They can have human sources or natural sources. Things like sea salt and soil and dust from volcanoes. These are natural sources. But then things like smoke and hairspray, they're human sources of aerosols. Aerosols are important because they act as a surface for water to condense on, and they're called condensation nuclei. Without condensation nuclei, you can't have precipitation. They also make the beautiful sunsets that we see. They absorb, reflect, and scatter the incoming solar radiation, creating the different hues of red and pink that we'll see at a sunset. The last variable component is ozone, the ozone layer specifically. Ozone is a combination of 3 oxygen molecules. And while there are chemical equations to explain why different particles will help to break apart ozone and make less ozone in our atmosphere, we're not going to get into it in this class. It's for an environmental science class. But ozone absorbs ultraviolet or UV rays from the sun, making our planet habitable for humans. As the ozone layer thins, it's it's not really like a hole in the ozone layer as you often hear. It's more if you think of felt. And as the ozone layer thins, it's more like the felt gets spread out and there's gaps in it that the UV rays can sneak through, rather than a single specific hole. So we've been talking about the sun and its effect on the atmosphere already, but we haven't really talked about how the Earth and the sun are related. Again, here are two terms. You've probably learned them when you were younger, but just refresh yourself. Rotation is the spinning around the axis between the poles of the Earth. This is what makes our daily cycles. Revolution is the Earth moving around the sun. It revolves once every year, and this makes our seasonal cycles. However, it's not just the revolution of the Earth that creates our seasons. We actually have seasons because the Earth is tilted. While our Earth is tilted, it changes the length of days throughout the year, and also the angle of the sun that reaches certain locations on the Earth. And so the incoming energy is changed due to the concentration of the sun rays based on the tilt, and also the atmospheric absorption. So if the sun rays have to pass through a lot of atmosphere, the atmosphere will start to absorb the sun rays, and the heat will not make it to the lower levels of the troposphere. Our Earth is actually tilted 23.5 degrees, and so the angle on Earth where the noon sun actually will hit at 90 degrees, it varies 47 degrees. So it varies from 0 degrees at the equator all the way up to 23.5 degrees north and down to 23.5 degrees south. We'll be going over this more in lab. I know this is not always the easiest thing to understand in just pictures and talk and verbal lecture. And so as the Earth moves around the sun, we end up getting a variety of locations where the sun hits the Earth at 90 degrees during noon. And this gives us 4 different days that relate to our seasons. You're familiar with summer, spring, fall, and winter, and this is just explaining why we have those seasons. So on the top and the bottom picture, where it says equinox, the sun's noon rays are hitting at the equator. Everything on the Earth is equal. Every location of the Earth gets 12 hours of daylight and 12 hours of sunlight. These are called the vernal and autumnal equinox. On the left-hand side, the sun is reaching at 23.5 degrees north, which is also called the Tropic of Cancer. Therefore, the most sunlight is occurring in the northern hemisphere. The North Pole at this time of the year gets 24 hours of sunlight, and the South Pole gets 0 hours of sunlight. This, when we refer to the northern hemisphere, is called the summer solstice. On the right-hand side of the picture, you have the opposite situation happening. The sun's noon rays are hitting the atmosphere hitting the Earth at 23.5 degrees south, or the Tropic of Capricorn. This situation gives the most sunlight to the southern hemisphere. In the northern hemisphere, we call this the winter solstice, and we get our shortest day of the year. Also, the South Pole has 24 hours of daylight, and the North Pole has 0. There are 2 more terminologies to take into account: heat and temperature. Heat is thermal energy. It's internal movement. It's quantity of energy. Temperature is the kinetic energy of atoms. It's intensity of energy. Heat transfers from warmer objects to cooler objects. This always happens. You're familiar with this if you put your hand on something hot and your hand will start to heat up. It's a very common occurrence, but it actually is one of those times in science you can say always. There are 3 ways that heat transfers. Heat transfers by convection, conduction, and radiation. Convection is circular movement due to density. So in this picture, the water at the bottom of the pot is heating up. It is getting less dense. It moves to the surface. As it moves to the surface, the denser, colder water will move downward. It gets near the source of heat, and it starts to heat up, causing a circular motion. I always think of a conveyor belt, or I think of running on a treadmill when I think of convection. Conduction is when heat is transferred through material by molecular activity. So conduction is when you hold a spoon and you're stirring a pot and the spoon gets hot and you have to drop it. The next one's radiation. Radiation is transferred through a vacuum of space. This is what happens with sunlight. It gets transferred through a vacuum of space and heats up the area that it reaches. You can also see this in the fire in the picture. That fire is heating all of the atmosphere around it. When we're talking about the sun, it's important to realize that there's a lot of solar radiation that is coming into our atmosphere that we are unaware of. We're often aware that our sun allows us to see the colors of the rainbow that we see every day, as if you go into a dark room, you can't see any colors. But the visible light there, you can see, actually takes up a very small portion of the solar radiation that comes in from the sun. This is called the electromagnetic spectrum, and it's the way to look at solar radiation based on whether it has short waves or long waves. Ultraviolet rays, which are just to the left of the visible light spectrum, are very important also, as we know, because ultraviolet rays are dangerous to humans. Infrared rays are rays that show off heat. So if you ever see a movie where they're looking through those binoculars that show off heat in a building and they can see bodies moving, they're looking at infrared heat. So there's a lot more radiation that exists out there than what we're often aware of. And we're not going to get too much into the electromagnetic spectrum, but it is important to understand that the visible light is only a small portion of the electromagnetic spectrum. As radiation comes in from the sun, it goes through a lot of processes as it passes from the sun all the way to that journey to the surface of the earth. It has to make it through clouds. It has to make it through aerosols. It has to finally reach the surface of the earth to start to heat up the surface of the earth. The most important number on this slide is that 50% of solar radiation finally reaches the surface of the earth and is absorbed. The other 50% is backscattered or reflected or radiated some other way, through the albedo effect or by being scattered by particles in the sky. If sunlight reaches water, it will be transmitted through the water, throughout the whole water body, or down to the ground. We often hear of the greenhouse effect and global warming. The greenhouse effect is a proven process that happens. It is the heating of the atmosphere due to incoming solar rays that are reflected off of the surface of the earth, get trapped by particles in the atmosphere, and then are reflected back down to the surface of the earth, constantly reheating the surface of the earth. Basically, short waves radiation comes in from the sun. When the waves are reflected off, they're reflected back in longer wavelengths, which can't penetrate the particles such as CO2 and water vapor in the atmosphere. And so instead of being able to move between them, they get trapped by it. This is what heats the lower atmosphere. It's actually heated from the surface of the earth, radiating back heat. It's not radiated directly from the sun always. Well, we'll look at this more in terms of global warming. Global warming is whether or not this process is increasing. Global warming is very much debated. However, the greenhouse effect is a known process that does happen on this earth. And that's the end of chapter 16.